Hello my dear students, welcome to Learning Chemistry is Easy and Fun. And what are we going to make easy today? Yes, it's the topic of crystal field theory, CFT, under coordination compounds. Really, it's become very easy. As we go along, you will see, and don't forget to keep a pen and paper in your hand to note down the important points and they become your notes. So let's start with CFT. Crystal field theory. I'll start this lesson with a question. Who gave the crystal field theory? Who is the main propounder of the crystal field theory? According to this theory, the bond between the metal or the central atom and the ligand is not a coordinate bond. On the contrary, it's a complete ionic bond. So this theory treats the central atom as the cation, the ligand which donates the electrons to the central atom as the anion, right? So we have the ligand is the anion and the central metal atom is the cation. The ligand, if it is the anion, they are called as point charges. For example, fluoride, chloride, bromide, such kind of ligands are called as point charges, or they are considered as point charges. They are not considered as big atoms. They are simply considered as charges. If on the other hand, the ligands are neutral molecules like water, ammonia, they are considered as dipoles having a positive and a negative end. And it is the force of attraction. Now the forces of attraction over here are the electrostatic forces of attraction between the cation and the point charge, which will be called as the ion-ion interaction, because one is a cation, one is an anion. So it's an example of ion-ion interaction. On the other hand, if we have interaction between a neutral molecule and the cation, the forces of attraction will be called as ion-dipole interaction. So ion is the cation and dipole is the neutral molecule. I have written it as dipole ion interaction because I have written neutral molecule metal interaction, right? Now, what the theory says is that when it has to form an ionic bond, the ligand will approach the metal atom, okay? And it's not just one ligand, there are a number of ligands approaching the central metal atom because they want to make friends, right? Now this central atom gets tense. Oh, who's coming? Who's coming in my way? Now when this central atom becomes tense, its energy becomes high, right? Just like as the exams are nearing, you are getting tense, so you are getting a little restless as well, right? So the same way, the central atom, its energy gets higher, right? Overall, the energy of it becomes higher. Now what will happen? Depending on how the ligand approaches, there will be changes in the electronic configuration of this central atom. And that is the crux of the crystal field theory, right? So the fourth point says that electron cloud of the cation and electron cloud of the ligand, they repel each other, causing the energy of the D orbital to be raised. Now, when the energy of the D orbital is raised, how do we go about it? Now for this, you need to see this structure. What I have done over here is I have simply taken 3 straws. You can take any spikes, anything, bamboo sticks. these are very easy to make. Now I have extended them in 3 different directions with the help of a rubber band. You could give me other ideas as well. I'm open to them. But this is the easiest I could think of. Now, what are these 3 perpendicular axes indicating? The x-axis, the y-axis and the z-axis. Why are we studying this? Because here the central atom is a transition element in which the electron is present in the d orbital. Your d sublevel is incompletely filled. Next step that you need to understand is the d sublevel consists of orbitals dxy, dyz and dxz. Why do we name them this way? Because here the orbitals are aligned in between the axis. So let's suppose I am saying this is my x-axis and this is my y-axis. My dxy is aligned in between them, right? That is why it is called dxy. Now this is x, y and z. If I am talking about let's say how I'm going to indicate, let's suppose I'm talking about dxz. Now in this case my orbital is aligned in between the x and the z axis, right? It is in between the two of them, correct? Same way, if we have dyz, then what will happen is my orbital will be aligned like this, right? In between the y and the z, correct? Now comes the interesting part. The other 2 orbitals, so we have the dz square. It's aligned like this along the z-axis. We talk about the dxy and the dx2y2. Here it will have the alignment along the x and the z-axis. This is how it is supposed to be, right? dx2, or let me put it like this, yeah, here. So now these are aligned along the axis. Now this is your dx2y2. When the ligand approaches, now first we said the ligand is, it's approaching from all directions like spherical. So it is approaching from all directions. To the energy, because of the repulsion, we always know that because of repulsion the energy level is raised. The energy level of all of these is raised, right? Then comes the interesting bit. Now in an octahedral complex, what is happening is the ligands are approaching along the axis. Now when they are approaching along the axis, it is the energy of the dz2 and the dx2y2 orbitals which gets raised much more than that of the dxy, dyz and dxz orbitals. So what has happened is the ligand earlier, my all 5 orbitals were like one common family, well knitted. Then came in the ligands. They started scaring them. Still they remained united, right? Although their energy levels became high, they became restless, they became a little scared, but still the energy levels were same. But because of the pressure of the ligands, what happened is they broke apart. 3 orbitals separated and formed one level, 2 orbitals separated and formed the other level. I'm talking about an octahedral complex right now. What about the tetrahedral complex? Do you want me to explain that as well? Okay, let me try and make it simpler for you. Just note down these points because here I bring something very, very interesting for you to understand. Let us start applying the crystal field theory to understand the splitting of the d orbitals in an octahedral complex. Now first you will have to imagine an octahedral complex. So where what we've got is we've got the 4 ligands in one plane. So you can imagine that this is one plane and your 4 ligands are 1, 2, 3, 4. And there are 2 ligands, one above and one below this, making it an octahedral complex, right? Now, second step you need to understand is the orientation of these ligands, right? So, I've got these 3 axes mutually perpendicular to each other. Now, in this case, 3 of my orbitals are arranged away from the approach of the ligand. So I've taken one example. So this is my dxy orbital, right? So if you see, it is aligned in between the 2 axes. And please remember, these 3 axes, they are same, all same. It's just for the sake of understanding that we have labeled them as x, y and z. And similarly, there's another one. So let's suppose this is xy and then you can call it as the xz because I will align it like this. Correct? Now here they are aligned away or in between the x, y and the z axis. There are 3 of them and this is how we represent it diagrammatically. So if we have these axes x and y, my dxy orbital is like this. If I'm talking about the yz, so just take it as yz, my dyz is like this. And how will xz be? Yes, the same way, but you'll have x and z over here. Sorry, x and y, y and z. You can also draw it 3-dimensional. It's okay. But what I'm trying to tell you over here is they are all 3 of them are equivalent in this case, and the lobes are oriented in between the axes. Come to dx2 y2, right? Your dx2 y2, how is it going to be oriented? Your dx2 y2 and dz2. Let us see that one. x2 y2, this is my x-axis, y-axis. x2 y2 are oriented along the x-axis. You can also call it as dx square y square. Same way, your dz square is this lobe oriented around the z-axis with a donut-shaped ring around it. And this makes our dz square. So you understand the difference in the case of dxy, dyz and dxz. These lobes are oriented in between the axes. So they are basically oriented here, right? My ligands are approaching along the axis. So the ligands here are approaching like this along the axis. Now when they are approaching along the axis, first of all, in the first stage that we spoke, the energy of all the orbitals is raised, right? Second stage is where these orbitals can't stand it any longer. The ones which are oriented in between the axis. They can't take the pressure anymore and they give in. So they are out of the race. So let us show it by means of this chart. So we have here, this is the central atom, ground state, degenerate, all the orbitals in the same energy. Coming to the approach of the ligands in a spherical field, this is the excited state, again all of them degenerate, correct? Next state, now this state is what we call as the barycenter. That means the level where the energy of all the d orbitals is assumed to be zero. They are all at equal energy. There is no difference between them, right? Due to the approach of the ligands along the axis, there's mutual distrust. These set of orbitals, their energy goes down. They say, okay, we can't put up the fight anymore, and we give in. So their energy gets lowered. By how much? For this we will calculate as 2/5 of delta 0. I'll come to that later. Whereas the two orbitals which are aligned along the axis, their energy gets raised. They're still in that fighting mode. No, we won't give in. We won't give in to these ligands. So they're full of energy. So they are raised to a higher energy level, right? This difference in energy of the orbitals due to the approach of ligands in an octahedral complex is called as delta O. Delta stands for difference and O stands for octahedral. So delta O stands for crystal field splitting in an octahedral complex. The energy of the T2G orbitals is lowered by 2/5 of delta 0, while that of the EG orbitals is raised by 3/5 of delta 0 or delta O. Now, if you see, I have used another notation over here, 4dq and 6dq. What is it? This crystal field splitting is measured in terms of a parameter called as dq. We are not to go into the details of it. So where delta 0 is equal to 10 dq, right? So if I am talking about the T2G orbitals, which are 2/5 delta O, I will have 2/5 of 10 dq, which gives me 4 dq as the value. In other words, the energy of the T2G, for every electron that enters into T2G, the energy will be lowered, it will decrease. Decrease with respect to what? The barycenter. So this decrease we can also denote by a negative sign in order to show that the energy is decreasing or the stability is increasing. And for the EG orbitals, again we can show it as 3/5 into 10 dq, which is equal to 6 dq. Here the energy goes higher than the barycenter and we denote it by a positive sign. What is this CFSE? Crystal Field Stabilization Energy. The difference in this energy of the split orbitals or the orbitals in the presence of the ligand from the state where they are all degenerate and all are of equal energy is what we call as crystal field stabilization energy, or simply put, the energy or the energy difference between the d orbitals in the metal atom when approached by a ligand from the metal in the isolated state is what we call as CFSE, or crystal field stabilization energy. Now, how do we calculate the CFSE? If I want to calculate the CFSE, crystal field stabilization energy, I need to know how many electrons are there in each of the two sets of orbitals T2G and EG. So let's start filling electrons into each of the sets of the d orbitals, in each of the two sets of d orbitals that we have here. When we fill the electrons, we will follow the rules that we follow for filling electrons in any isolated atom as well, right? So Aufbau principle, Hund's rule, all those rules will be applicable when we fill in the electrons here. So let's start doing that, and let us also calculate the crystal field stabilization energy in each of these cases. As the name indicates, it is the energy which accounts for the stability of that particular complex ion. D1 means the electron enters into one of the T2G orbitals according to the Aufbau principle. So what we'll have over here is CFSE. In order to calculate, the energy falls by 4 dq. So it is simple, 4 into 1, that is minus 4 dq, right? You could also show it as minus 2 by 5 delta O into 1, that is equals to minus 2 by 5 delta O. Both mean the same thing. How about D2 configuration? Please keep on making a note of this side by side. So D2 means whether there will be pairing or will it be going to the next orbital. Yes, it will be going to the next orbital because orbitals are first singly filled and then pairing begins. So what we'll have over here is minus 4 into 2 gives us minus 8 dq. That means when an electron from the ligand enters into this, the energy gets lowered further by minus 8 dq, right? Go on to D3. Again, the electron enters into dxz. What will be CFSE over here? Minus 4 into 3 gives us a value of minus 12 dq, right? So far so good. Now comes the case where the fourth electron has to enter. I've got a configuration D4 and we are taking that all the electrons are coming from the ligand. Now, when it is D4, will the electron, the fourth electron, go and start pairing, or will it go over here? What do you think? Now here, something interesting happens. Actually, both the possibilities are possible. Option 1 and option 2. Right? What are those two options? Option 1, the electron goes and enters into the dz square orbital, right? Into one of the EG orbitals. right? When will this happen? That means these electrons are not allowing it to pair up, you know. They're very unfriendly. They say, we don't want to make friends with you. You go away from here, right? So this has no option but to go into the higher energy level, right? In other words, they are not allowing pairing to happen. We have option 1, wherein the pairing energy is much higher than the octahedral splitting energy, right? What do you mean by pairing energy? There's another term that I am introducing. So many new concepts to be understood, right? Don't worry, at the end of this, I'll give you some easy trick. But you need to understand first. What is pairing energy? The energy required to pair the electrons, right, in the lower orbitals. So if pairing energy is higher than the octahedral splitting, then what will happen? No pairing will take place because it's easier for this. In other words, your octahedral splitting is small. These orbital differences are small, due to which the new electron can easily go and enter into the EG orbital. So it doesn't put up much fight and doesn't force them to pair up, because anyway it says I need a lot of energy to make friends, so why bother, let me go on to the next one. Anyway, that door is also nearby. Such ligands which show this kind of a behavior are known as weak field ligands. That means those ligands are weak. They don't bother much about pairing up. And such complexes are called high spin complexes, where the electron goes and enters into the higher energy level, and you have more electrons which are unpaired, and unpaired means more is the magnetic character. Now in this option 1, can you calculate the CFSE? That is the crystal field stabilization energy. Now if you notice, you've got 3 electrons with -4 dq. So you have 3 into -4. And you have 1 electron contributing a positive energy of 6 dq. So 6 dq. And we are left with -12 plus 6, that is equals to -6 dq. Overall, a decrease in energy and denoted by -6 dq. Right? Would you like to calculate on the basis of this same option 1, would you like to calculate the CFSE for D6 configuration? Right? So D4 we have already done. Where will D5 now go? Obviously, it will go to make it half filled. Now what about D6? Yes, again the pairing will begin from the lower energy orbital, right? Now calculate the CFSE. So we have 1, 2, 3, 4. 4 electrons contributing to -4 and 1 and 2. 2 times 6 gives us 12. So -16 plus 12, what do you get the answer as? Very good. Perfect. Right? Okay. Now let us look at option 2 and when does it happen. I hope you are clear with this. Would you like to note this down? Don't worry. I'm promising you, it looks confusing, but I have simplified it for you in a very, very easy way at the end of this topic. But as I said, from examination point of view, you need to understand. From entrance examination point of view, you need the tricks, which I'll give you. But for present, understand this. Let's look at option 2. What if the pairing energy is small? That means there is very little energy required to pair. So let's look at those options as well. Now 1, 2, 3 electrons entered. That's it. Okay. That remains the same. What about the fourth electron that now wants to enter? Now your ligand field was very strong. So what it did was it separated the two of them very much. So the ligand cannot go and jump into EG. It has to put up a fight and cause the pairing to happen. In other words, we need very less energy to pair compared to the crystal field splitting. So the crystal field splitting here is greater compared to the pairing energy. So the electron now starts pairing up the electrons in the T2G set of D orbitals. This happens when the ligand field is strong. So we say strong field ligands cause pairing, and such type of complexes are called as low spin complexes. Now would you like to calculate the CFSE? I'm sure it's fun now. It's easy, right? 1, 2, 3, 4. 4 into 4 or 6? Very good. It will be into -4. So CFSE comes out over here. 4 into -4 d cube. That is equals to -16 d cube. Now this is a very simplistic view, okay? Because as you go to the higher levels, this becomes more and more complex. But as a beginner, this is just right, okay? I'm not going into too much complexities. I don't want to confuse you. Same way you can calculate for D5, D6 configurations. Once this is full, then the electron starts going into EG, right? Now, what are the factors which decide whether it's going to be option 1 and option 2? Very simple. Of course, the answer is there right in front of you. Whether the ligand is a weak field one or a strong field one. So it's the nature of the ligand, right? Second, of course, is your central atom, in what oxidation state it is in. What is its size? These factors go on to decide whether we are going to have a weak field or a strong field complex. Also, there is a series called as the spectrochemical series, based or deduced on the basis of the absorption spectrum, what we call as the spectrochemical series, in which we are going to list the weak field ligands and the strong field ligands. Now what I have done is actually option 1 and option 2 I have depicted by means of this chart. So probably you may want to note it down, so it makes the concept a bit more clearer for you. So from here you can just make a note of this. EG and T2G, option 1 where they separate and go into EG, option 2 where actually pairing happens, right? If pairing energy is high, it goes into EG, whereas if pairing energy is low, it starts pairing up, right? We will now extend our concept of octahedral complex to, yes, perfect, tetrahedral octahedral complexes. But before we go on to do that, please make a note of this so that your notes are ready for future reference, especially when you are offline or preparing for examinations. Let us now try and extend our learning of octahedral complexes to the next type of complexes, coordination compounds, and that is the tetrahedral complexes. Tetrahedral complexes means coordination number is 4. Coordination number 4 means how will the ligands be directed? Yes, they will be directed like this in a regular tetrahedron, right? Now, in this case, if you see the ligands, they will approach this particular complex from a direction which is, yes, it is along or in between the two axes. My axes were like this, correct? 1, 2 and 3. But how are my ligands approaching? In between the axes. Now, because the ligands are approaching in between the axes, it is the energy of the dxy, dyz and the dxz orbitals which gets raised. dxy, dxz and dyz. So, and those of the dx square y square and dz square gets lowered, right? So basically what has happened is the situation has completely flipped. This is what we had in the case of an octahedral complex. 3 down, 2 up. For a tetrahedral complex, it's totally reverse. It's 3 up and 2 down. I've introduced a new term over here, barycenter. Now this barycenter, it's not that it was not there in the octahedral complex, but there were too many new things. What is this barycenter? It's this hypothetical level of the d orbitals where their energy is assumed to be 0. It's just before the splitting. The energy of the Eg orbitals here is getting lowered by 6 dq, whereas those of the T2g is getting raised by how much? 4 dq. Now, if you remember, again reminding you of the octahedral, again it was 6 dq up and 4 dq down. Here it's like, yes, you just flipped it. Next, coming to, so the energy, the crystal field splitting is represented as delta, indicating difference or change, T for tetrahedral. What had we used in the case of octahedral? We had said delta O. Delta is the change or the energy difference, O for octahedral. What is the relation between delta O and delta T? Delta T is much less than delta O. In other words, the crystal field energy in the case of a tetrahedral complex is lower than that for an octahedral complex. So, that means when I am talking about pairing, right? So, delta T is would be definitely much less than the pairing energy over here because it's anyway less than delta O as well. So what would be preferred over here? So if I have to fill electron 1, 2. Now next would be the electron enters into the higher energy level or it pairs up over here. You tell me how we are going to accommodate the third electron. So if I have D1 configuration, electron goes here. D2 electron configuration means electron goes here. If I have D3, the pairing energy is large, delta T is small. So anyway, the electron enters into the T2G. So what type of complexes are these? Yes, they are all high spin complexes, which I have in short form written as HSC, just for short form, just for easy recall. Because here the tetrahedral splitting is much lower than the pairing energy, or you can say vice versa, that the pairing energy is much higher. The energy required to pair the electrons is much higher than the tetrahedral crystal field splitting. Right? Have you noted this down? Can you try and write the definition of barycenter for me here? We are now going on to the splitting of the d orbitals in a square planar complex. I know it is beyond the scope of the present study, but it's something interesting. I'll just touch base and then we will bring an end to the lesson by giving you something which will help you to recall things easily. Square planar, right? The spikes are in the form of a square. So we have the central metal atom, we have the ligands and the four corners of a square. Now the splitting of this is a little more complex, so we do not usually deal with this at the senior secondary level. But I have depicted over here the splitting of the D sublevel into the orbitals dyz, dxz forming the base, dz square, dxy and dx2 y square, right? Because you can very clearly see that the ligands are definitely approaching along the axis, right? Spectrochemical series. Arrangement of ligands in the order of their ability to cause the splitting of the d orbitals is what we call as the spectrochemical series. We start with the ligands which have that weak strength, which are weak field ligands, and end with the strong field ones. What is the difference? Let's go back to what we had done under the octahedral complexes, and we had said that pairing will take place if it's a strong field ligand, and if it's a weak field ligand, the electron enters into Eg. When it's a weak field ligand, it results in high spin complexes, and when it's a strong field ligand, it results in low spin complexes. Strong field means the energy difference between the two Eg and T2G will be large as compared to in this state. What type of ligands are strong field or low spin complexes? They are pi acceptors. They'll accept electrons through pi bond, but they will donate electrons through sigma. They have easy tendency to donate electrons. On the other hand, the weak field or the high spin complexes, on the other hand, donate electrons by pi. They don't easily want to do away with their electrons. So we have the highly electronegative elements which are at the beginning of the series. Iodide, bromide, chloride, fluoride and so on. How to remember them? Actually, there are a lot of anomalies, but what I have observed personally is the weak field or the high spin complexes are usually, or the ligands are usually those wherein the donor atom is belonging to group 6 and 7. But again, I repeat, there are anomalies in this. So for example, iodide, bromide, the sulfide atom in SCN, chloride, sulfide, fluoride, all these are high spin weak field complexes because they don't want to do away with their electron pair. On the other hand, at the end, or what we say at the top of this series, what we have is, we have the strong field. So we have the NO2, CN, CO and so on, which have a strong tendency to form multiple bonds, but at the same time they can donate electrons easily. These you will find wherein the donor atom is usually belonging to the group 4 or group 5 in the periodic table. Sorry, to be more appropriate according to the modern system, we will have group 15 and group 16, and sorry, this was according to the older system, and this is group 16 and group 17. So this is group 14 and group 15 of the periodic table, right? Now, if the splitting is large, for example, we have seen in the case of strong field ligands here, in the case of strong field ligands, because the splitting is large, it is the pairing of electrons which takes place. Now, because the electrons pair up over here, the number of unpaired electrons in a low spin complex will be less compared to the number of unpaired electrons in a high spin complex. Now, does that ring a bell? Unpaired electrons. Can you recall something from the valence bond theory? Yes, the magnetic character. So, more the number of unpaired electrons, higher or stronger will be the magnetic character compared to where all the electrons are paired up. This explains why our weak field ligands or weak field complexes or high spin complexes are more magnetic as compared to the low spin ones, right? Can you try and find out the explanation for the color observed in the case of coordination compounds based on crystal field theory? We'll get back to that in lesson number 7 of coordination compounds, where we are going to talk about the applications of crystal field theory. Stay subscribed and do share the joy of learning with your friends and classmates. See you soon.